Welcome everybody, my name is Jan Pennekamp and I'm going to present you our paper Privacy Preserving Production Process Parameter Exchange. So this is joint work with colleagues from the Laboratory for Machine Tools and Production Engineering and Institute of Plastic Processing, both in Aachen. First of all, I'm going to give you a little bit of an introduction about the Internet of Production. So we're a federal funded research cluster here in Aachen where over 35 institutes from different disciplines are participating, and the goal is to create a worldwide lab. So we want to utilize information from different production steps globally. Eventually, we want to establish a Google-like engine for production queries where we kind of utilize all the available information. Now, to illustrate that, it would look like that. We have different model factories here in Aachen that can be interconnected, but we also have interregional ties that can be integrated. The goal of our research is to improve the collaboration of all these different stakeholders that are participating. Now, for the sake of this talk, we're considering the following problem statement. While we have all this information available locally, we have a lack of data sharing between different companies. So a lot of domain-specific knowledge is only retained locally, and thereby potential to improve processes is wasted. Now, what we need is a way to exchange this information. Currently, there is no privacy-preserving way to do this, and therefore companies have concerns about participating there and potentially even like incentives to do so. So we require a solution that addresses these needs and also is secure at the same time. Now, for this talk, we're going to consider a use case in the domain of injection molding, where the current best practice to set up new production lines is to use resource-consuming empirical testing. So with resource-consuming, I mean time, material, and machines alike. And this process results in quite some waste because the machines are reconfigured and then a new batch is tested and so forth. Here, a lot of improvements are expected by utilizing transfer learning. However, we require a training data set to apply this transfer learning. And the issue here is that we might not have the best effective data available locally because it might only be available at another company or stakeholder. So we're in need of a privacy-preserving approach to change that, and this should even work between mutually distrustful companies. Now, for our privacy-preserving exchange, we have the following design goals. On the one hand, we have the provider privacy. We're interested in maintaining their competitive advantage and not sharing all their information and data publicly. On the other hand, we have the client privacy, because the client is also interested in keeping his queries, so the request of retrieving new parameters, private. So centrally, we have this exchange platform that should obviously match the client queries with the parameters that are available from the providers. Now, how does that work? So initially, the providers kind of share their known parameters, and in return, they expect some kind of payment for the items. On the other hand, the client first wants to compute similarity metrics, so identify the parameters that he's interested in, and this is also sensitive information as it might be his competitive advantage over other companies or clients. And then once he identified those items, he requests them and only receives the intersection of the available and requested items from the exchange. Now, for the exchange itself, we also have 3 additional design goals. So it should, of course, be deployable in the real world. Then the performance should satisfy use case specific needs. And it should finally be adaptable in terms of security and privacy according to the available use case. Unfortunately, related work is not suitable to be used here. So existing solutions either focus on client privacy or provider privacy, and most of these approaches do not scale to industry needs. So therefore, we develop an applicable design ourselves, which I'm going to present in the following. So we propose a Bloom filter based parameter exchange called BPE. We have an exchange platform that consists of two different servers. So first, we have the key server that generates encryption keys for the parameters once. Those encryption keys are then requested during the data provision phase from the data providers, who locally themselves encrypt the parameter records. Those encrypted records are then offloaded to the storage server that maintains the Bloom filter to index all the available parameters that are stored at the storage server. Then clients can, during the matching phase, retrieve this Bloom filter and use it to conduct the matching, basically to compute the similarity metric and check whether parameters are indeed included at the exchange platform, and if they are also in the Bloom filter. Then, during the record retrieval, the client first requests decryption keys for those records that matched, and then requests those records from the storage server. Using the records and the decryption keys, he can eventually decrypt the records and get access to the parameters that he is interested in. For all the details on the notation, protocol specifics, and our security assumption, I would like to refer you to the paper, mainly due to time constraints in this presentation. Now, continuing with the evaluation, we follow a fourfold approach to underline our solution's feasibility. First, we survey the building blocks that were used on its own, then evaluate on an artificial scenario, and furthermore consider two real-world use cases. For time reasons, I will skip the building block evaluation in this presentation and only focus on a single real-world use case, which considers the exchange of production parameters of toy bricks. Here, the whole process of retrieving the parameters and applying the transfer learning may take up to several weeks, even in real-world deployments. Now, continuing with the artificial setting. So here, we first look at the provision phase, so where data providers offload their parameters to the platform. So with an increasing number of records, the runtime increases. However, as we can see, the provision time is basically irrelevant because it's quite fast and it constitutes a one-time operation per data provider anyway. Continuing with the querying phase, which is triggered by the client, we can observe a similar behavior. So with a larger number of matched records, the runtime also increases. However, we notice that the matching phase takes most of the time here. So depending on the used similarity metrics to identify relevant parameters, the matching phase can be quite significant. So for this example here, the client tests 29 million parameter sets for inclusion in the Bloom filter. So we can conclude that the number of matches has a negligible influence on the performance because the matching phase takes most of the time. The good thing here is that the matching phase is completely done by the client itself, so it does not burden the exchange platform. Continuing with our real-world example in the domain of injection molding, we've already seen that the candidate set can be quite large, and this is driven by the used similarity metrics. So for the sake of this example here, we're going to consider two different metrics. One with a relative offset of 2% and another one with 2.5% for each parameter. Here we use 21 identifying parameters that then return records with 28 detailed entries. So the 7 parameters that are kind of retrieved from the exchange platform would here be 6 essential machine setting parameters and another parameter or quality indicator. The exact distribution of those aspects depends on the use case. Now, When evaluating this setting, we can see that again, the matching phase constitutes most of the runtime. So for our relative offset of 2%, we have a candidate set of only 1 million possible matches. However, this increases to more than 100 million entries for relative offset of 2.5%. However, this also concludes in under 2 hours. So this is definitely scalable, and even larger offsets or different similarity metrics seem feasible. Again, the conclusion is that the client runtime dominates our approach. So overall, it does not burden the exchange platform itself. So if you're curious and would like to know more, we have, among other things, a security discussion, a second design variant utilizing private set intersection, and a second use case in the paper. Now, to conclude this presentation, we've seen that approaches for industrial data exchanges are currently missing, and because this information is only locally available, a lot of potential is wasted. To address this, we propose BPE, our parameter exchange, which addresses industry needs and is both scalable and universal at the same time. We demonstrated BPE with 2 real-world use cases, of which one I presented here in this presentation. With BPE, we account for the needs of tomorrow's industrial landscape because we, unlike real world, consider both client and provider privacy. And with this, I would like to conclude my talk and thank you for your attention.